Hello, if you've ever been on social media and you tried to talk to a flat earther, they'll try to give you all sorts of excuses why they think that things work on a flat earth. And one of the things that they will say when you bring up the problem of angles to various objects like Polaris or the sun is they'll say it's all due to perspective. In fact, if you ask them if the sun is always above you, how can it appear to set and go below the horizon? They will give you some sort of excuse like it's perspective. A few weeks ago, I happened to be driving around the west end of Ottawa, and I thought this would be a good opportunity to take a slight detour to the marina that I've gone to a few times before and use one of the lamp posts that were there to run an experiment. In essence, I thought that I would make an observation to see just how well the flat earth idea of perspective would stand up to scrutiny. So the process was fairly simple. I started off at one particular spot and I pointed my theodolite to the base of the lamppost and I got an elevation reading, and then I would point it to the top of the lamppost and I would get another elevation angle reading. I would walk ahead some small distance and repeat the process, and I kept repeating the process. Later, I entered all of the GPS readings that the Theodolite app reported into a spreadsheet along with the angle elevations to the base and to the top of the lamppost. And that would be this over here. For these columns, I normalized the angle so that if I'm on the left looking towards the lamppost to the right, that I could use the angle that GIMP reports like this, so that I could end up finding the appropriate pixel location in this image, which would be an equivalent representation of where I was standing. I used an online tool to enter two geocoordinates, and I asked it to compute the distance between them in feet. So in this case, I manually entered those values in from that tool. Here I subtract the one angle from the other, and the one being below my horizontal. So in essence, I'm really adding it to the other angle, and this is the full angle deflection. I then got the Haversine formula that I then entered into these cells over here so that I could then calculate the distance myself. And since the formula had this expressed in meters, I converted meters to feet. I used kilometers and I divided that by 1.609, then multiplied by 5,280 to give me 20,906,699.81 feet for the radius of the Earth. And so with that, I was then able to calculate the distance in feet between these two geocoordinates. So one of the simple goals was to see if I could calculate the height of the lamppost strictly by the geocoordinates and the angle measurements to each of those 2 points on that lamppost. So I made a few assumptions and I simplified the process. I assumed for a minute that I was on fairly level ground. If I knew the distance between these 2 points and I had these 2 angle measurements, I could then calculate the length of the hypotenuse. And once I had the length of the hypotenuse and this angle, I could then calculate the height above my eye level at the lamppost. And I did the same operation for below my eye level. So in this case, 6.3 would have been this angle. 171.3 would have been the difference between 180 degrees and 8.7. And then solving the triangle for 2 angles and 1 side, I was able to calculate the length of the other sides with the math and the calculation steps that they provided here. This set was to calculate the height of the lamp post below my horizontal eye level. This set was to calculate the height of the lamp post above my horizontal eye level. And I added those 2 values together to come up with a grand total. And after all of that effort, as very crude and hastily done as it was, I was quite pleased to see that the average height was close to the height that was posted on a plaque on that lamppost. Sometime later, I decided to redo my test in another location. I happened to be coming back from visiting family, and I decided to pull over and repeat the process in a much more hastily measured way. Here is the result. And in a very similar way, I was able to ballpark the height of that lamppost at around 26 or 27 feet. The process was similar, and I am certain that if I took much more care in taking the measurements and arriving at a height, that they would all be much closer to the average. I know that flat earthers have absolutely no answer to this, but I just have to ask the question. If I took various readings like this and I applied simple math and got fairly consistent results, at what point does light stop behaving the way it does and start behaving the way flat earthers think that it does? Well, that's going to be it for now. Thank you for watching. If you like the video, you know what to do. With that, I'm going to see you again in another video at some point soon enough, I hope. Bye for now.